Hello everyone, welcome back in Scholar Hive. So this is the fourth lecture in our basic algebra series, and this is the second part of polynomial. In lecture number 1 I already covered the first part. If you have not watched that, I'll suggest you to go through that. So today in this video we are going to learn the zeros of polynomial, then the divisions of polynomials. After that we'll cover the remainder and factor theorem. So let me start today's session with the zeros of polynomial. Zeros of polynomial. What exactly the meaning of zeros of polynomial? Let me start with one example. Let's say we have given a polynomial p in variable x as x plus 6. So if I'm asking you to find the value of px for different values of the variable x, let me just start with some of the different values of x. Let's say if I'm taking x0, then p0 will be equal to 0 plus 6 is 6. If I'm taking this value of x to be 1, then that is going to give us p1 is equal to 1 plus 6 is 7. If I'm taking this p minus 1, that is going to give you minus 1 plus 6 is plus 5. Likewise, we can find different values of this polynomial px at different values of x. But out of those values of x, we'll find some values of x which is going to give the values of this polynomial to be 0. Let's see if we are further finding the values at different values of x. We'll find different values of px. Let me take the value of x to be negative 6, so which is going to give us negative 6 plus 6 is equal to 0. So we found that at x is equal to negative 6, the values of this polynomial is equal to 0. So that value of x is known as the 0 of the polynomial. So here we can say that x is equal to minus 6 is 0 of px. 0 of px. So write down the definition. What the meaning of 0 of polynomial? The value of variable at which the polynomial value is 0. Value is 0. The value of variable at which the polynomial value is 0, that value of variable is known as the 0 of polynomial. If we have a polynomial px and that px is equal to 0 at x is equal to a, then x is equal to a is 0 of px. So in order to find the 0 of a given polynomial, we need to just equate that px is equal to 0, and then we need to solve the equation for the value of x. Let's try some example for finding the zeros of a linear polynomial, and then we'll see some example of finding the 0 of a quadratic polynomial. Find 0 of px. We have given px is equal to negative 3x plus 9. So as this is a linear polynomial, in order to find the 0 of this, what we need to do? We need to just put the value of px is equal to 0, and then we need to solve the equation for the variable x. Now px is given as negative 3x plus 9, which is equal to 0. So it's a linear equation in one variable, so you can easily solve by using the transposition. So we can get it as this is equal to negative 9, so x is equal to, cancel both sides by negative 3, that is going to give us x is equal to 3. So x is equal to 3 is the 0 of this polynomial. You can try by substituting the value of x over here and check whether at x is equal to 3 is going to be 0 or not. If you are putting x 3, then minus 3 times 3 is minus 9 plus 9 is going to be equal to 0. So this way we can find the 0 of a linear polynomial. So let me just take the standard form. Let's say px is equal to ax plus b. Here a is not 0. So this is the standard form of a linear polynomial. In order to find the 0 of a linear polynomial, we just use this direct result, or we can go for solving the simple equation as well, but are correct only. So if I'm taking this px is equal to 0, then that means what? Ax plus b is equal to 0. Now shifting this b to the right, that is going to be negative b. So x is equal to negative b over a. So for linear polynomial, the 0 is given by negative of constant over the coefficient of the variable x. Okay, so this is the 0 of a linear polynomial, any linear polynomial of this form, where a or b might be positive or negative, but the condition a should not be 0. Now let's try to solve couple of questions based on like finding the unknowns if we have given zeros of a polynomial. Find the value of unknowns. First example, if x is equal to negative 1 is 0 of px is equal to kx square minus x plus 2. Then find value of k. So here we have given x is equal to negative 1 is 0 of px. Then we need to find the value of k. So x negative 1 is 0 of px. It means what? At x is equal to negative 1, that px value will be 0. Means this value will be 0. So substitute the value of x equal to minus 1 in the given polynomial. So this p negative 1 is equal to what? K times of negative 1 square minus of negative 1 plus 2. As x is equal to 1 minus 1 is 0, it means at x is equal to minus 1, this p negative 1 will be equal to 0. So it means this is equal to 0, and this is k times negative 1 square means positive 1. Positive 1 into k is k. Now here minus minus is plus 1 plus 2. So we are going to get this as k plus 3. So the value of k we can find by transposing this to the other side. So this is negative 3 is the value of k. Okay, this is the way we can use the concept of the 0 of a polynomial for finding the unknown. So make sure to understand what exactly the meaning of 0. 0 means not the like px value. We need to look for the variable value at which the px value is to be equal to 0. Now let's try to solve another question based on the 0. Let x is equal to 1 and x is equal to minus 1 and x equal to 1 are 0 of px is equal to x cube plus 2x square plus ax plus b. Find value of a and b. Find value of a and b. So we have given x minus 1 and x is equal to 1, both are 0 of this polynomial. Okay, and we need to find the value of a and b. It means if x is equal to minus 1 we are keeping in this polynomial, means that is going to be equal to 0, as this is zeros, and the same way we'll keep x is equal to 1, that is going to give the px value to be the 0. In this way we'll get two equations in two variable. We need to solve that by using any of the method. I'll discuss the method of solving the pair of equation in two variable. So let's see what is given. If we are looking for p negative 1 at x is equal to minus 1, so just substitute the value of x to be negative 1 over here. So negative 1 part 3 plus 2 times of negative 1 part 2 plus a times negative 1 plus p. As this is 0, it means this is equal to 0. So p minus 1 is 0, which is equal to this minus 1, and minus 1 square is plus 1 into 2 is 2 plus 2, and this is plus minus is minus a plus b. So once we simplify this minus 1 plus 2 is plus 1, right? So we are going to get this as 1 minus a plus b. So further when we simplify this, shifting this 1 to the right side, that is going to give you minus 1 is equal to minus a plus b. This is equation number 1. This is equation number 1. Now x is equal to 1 is also one of the 0. So if we are keeping p1, it means that is going to give us 1q plus 2 times of 1 square plus a times of 1 plus p, and this is 0 as this is p1 is 0, right, of polynomial. Means at x is equal to 1, p1 value is 0. Now this is 1, this is 2 into 1 square is 1 into 2 is 2, a plus b. So this is going to be 3 plus a plus b is equal to 0. Now minus 3 is equal to a plus b. This is the equation number 2. We have got two equation in two variable. First equation is minus 1 is equal to minus a plus b, and the second equation is minus 3 is equal to a plus b. So how we can solve this? So for solving the equation in two variable, we have different method. One is substitution method, one is elimination method, and one is cross multiplication method. So I'll discuss with the help of substitution later on when we will deal the pair of linear equations or system of equation. That time we'll discuss rest of the method. So here what we can do, we can solve any one equation for one variable. Let's say if I'm finding the value of a or value of b from this equation in terms of a, and that value of b if we are substituting in the second equation, then that will be an equation in one variable, and easily we can get the value of the variable b. So let's try to solve this for b first. If I'm just taking this minus a to the left side, that is going to be plus a minus 1 is equal to b. So that is going to give us from this equation we'll get a minus 1 is equal to b. The value of b is equal to a minus 1 we have got, right? Now this value of b need to substitute in the second equation. So then this will give us what? Negative 3 is equal to a plus in place of p we need to keep a minus 1. So a minus 1. So that is going to give us minus 3, minus 1 goes over here, plus 1, and here this is 2a. So this is minus 2 is equal to 2a. So when we solve this, that is going to give us, by dividing both sides by 2, that will get as minus 1 is equal to a. So the value of a is negative 1. Value of a is negative 1. So once we substitute this value of a in this, then we'll get the value of b. So if we are keeping a is equal to minus 1, so minus 1 is minus 2. So the value of b is equal to minus 2. Now let's try to solve some more question based on zeros of a polynomial. Let p be a polynomial, p be a cubic polynomial such that p0 is equal to k, p1 is equal to 2k, p minus 1 is equal to 3k, and if p2 plus p minus 2 is equal to m times k, then find m plus 3. So we have given a cubic polynomial such that values of polynomial at 0 is k, value of polynomial at 1 is 2k, and at minus 1 is 3k. Further, we have given this condition: the sum of the values at 2 and minus 2 is equal to m times of k. Then we need to find the value of m plus 3. So as the polynomial is cubic, so let's the standard form of the cubic polynomial. So let's pxb is equal to ax cube plus bx square plus cx plus d. The condition that the leading coefficient should not be 0. Now as the value of p at 0 is k, so we just have to substitute the value of x is equal to 0, 1 and minus 1, and then we'll get some equations in a, b and c as well as d. So first substitute the value of x0. When we are putting x0, then p0 is equal to what? K. So k is equal to, now if you are putting 0 over here, 0 power 3 means 0 into a is 0, this is also 0, this is also 0, only the constant term will be there, so k is equal to d. So this is the value of d. Now let's substitute the value of x is equal to 1. So when we are putting x1, then this will be equal to a plus b plus c plus d, and p1 is 2k, so 2k over here, a plus b plus c, and as t value we got it as k, so we need to substitute that value, and then further we'll simplify, sending this to the left by transposition. We get it as 2k minus k. 2k minus k is equal to a plus b plus c. So 2k minus k is what? K. So this is the sum of a, b and c is equal to what? K. So mark it as equation number 1. Now we have given p negative 1 is 3k, so substituting x is equal to negative 1, so that is equal to a times x to the power 3, means it's negative 1 to the power 3. Negative power odd is odd number, right? Is negative number, right? So that is going to be equal to negative 1, because minus 1 power 3 is minus 1, and then b times of negative 1 power 2 means positive 1, right? C times of negative 1 plus d, and this value is given 3k, so 3k is equal to negative a plus b negative c plus d, and as the d value is k, so when we substitute the value of d to be k, so this is negative a plus b negative c plus k, so transposing this to the left, that is going to give us 3k minus k is equal to negative a plus b minus c. So 3k minus k is nothing but 2k, so 2k is equal to negative a plus b minus c, right? Negative a plus b minus c. So this is equation number 2. Now look into this two equation 1 and 2. We got a plus b plus c is k, minus a plus minus b is minus a plus b minus c is equal to 2k. So if we look carefully, we are adding the right side of this equation, both of this equation, then plus a minus a going to be cancelled, right? Plus c minus c is going to be the cancel, right? Then only plus b will be 2b. From these two equation, if we are adding these two equation, we'll get the value of b then, right? We'll get the value of b. So let's try to solve this further. So 2 plus 1, adding this equation 1 and 2, what we'll get? So here negative a plus b negative c, in that I'm adding the first equation, which is a plus b plus c, and the value of this is 2k plus k. So minus a is got cancelled, minus c plus c got cancelled, so we are getting this value as 2b is equal to 3k. So from this we are getting b is equal to 3 over 2 times of k. So now we got the value of d, which is k, we got the value of b, which is 3 by 2k. So further, if we are substituting the value of b in these two equation, and after solving these two we'll get the value of a and b, but which is not required over here. We have given further more condition, p2 plus p minus 2 is equal to mk. So try to evaluate this and then simplify, we'll get the result. Okay, so what we have given, p2. So p2 means what? In place of x we have to substitute 2, so then 2 power 3 means 8a, 2 power 2 means 4b, so this is going to be equal to 8a plus 4b plus 2c plus d, right? And p negative 2 is going to give us here negative 2 power 3 means negative 8a, so this is negative 8a, and then plus 4b, and this is minus 2 plus minus is minus, because if we are substituting x is equal to minus 2 over here, so minus plus minus, right? So that is going to give us negative 2c and then plus d. Add both of this, so p2 plus p minus 2 is what? This 2 plus minus got cancelled, this plus minus got cancelled, so 4b plus 4b 8b, and d plus d is 2d, and we got the value of both d as well as b. If we are substituting the value of b and d in this, then we are done. As this value is given as mk, so m times of k is equal to 8b plus 2d. In place of b we can substitute this value 3 by 2, so this is 8 times 3 by 2k plus 2 times of k, so which is equal to mk is equal to 4 times, so 4 3 is 12k plus 2k, so this is equal to 14k is equal to m times of k. Now k got cancelled, we get m is equal to 14, so the value of m is 14, so we can say that this m plus 3 is equal to 14 plus 3 is 17. M plus 3 is what? 17. So this is the way we can solve the question based on the zeros of a polynomial. Okay, and for that we need to know the standard form of the cubic polynomial, quadratic polynomial, and linear polynomial, right? And the process how we are finding the zeros of a polynomial. Now let's move to the next part, which is division of polynomial. Division of polynomial. Divisions of polynomial, in which we are going to discuss the long division method and division of polynomial by using factorizations or synthetic methods will cover at last in this polynomial series. So for the long division, first let me explore an idea of long division with the help of positive integer. Let me take an example. Let's say I'm dividing this 44 by 6. So we need to look for a whole number over here that is going to give the value which is either equal to this or nearest to this number, right? So that is going to be 7. So 7 times is 42. And then once we subtract, then we'll get this as 2. So in this one we call as remainder, and this, this is the divisor, right? This is quotient and this is dividend, right? So in earlier classes like 4th or 5th standard, when you people are doing the long division and after that you are verifying your result, right? So what you used to do, so that was like dividend is equal to divisor times quotient plus remainder, right? This is what you used to verify the result, right? You can cross verify. This 44 is equal to what? Divisor is 6 times of quotient, which is 7, plus remainder 2. 6 sevens are 42 plus 2, which is equal to 44, right? So this way we used to do the division, a long division method, and the verification like this. So if I'm just extending this for any positive integers, so then you can find that one thing is over here, this is the remainder that will always be less than this divisor, right? So we have one important result that we call as division lemma. Division lemma. For example, let's say we have a positive, any two positive integer, a and b. For any two positive integer a and b, if we are dividing a by b, then we'll get two unique integers. We'll get two unique integers, so that are q and r. That q and r are nothing but this is the quotient and the remainder. So when we are dividing this dividend by this divisor, we are getting two integers. One is quotient, one is remainder, right? So what it says that this dividend is equal to this divisor into quotient plus remainder, and the remainder might be 0. This remainder might be 0, or this might be less than the coefficient over here, which is the divisor, right? B. So the r value is either equal to 0 or greater than 0, but it must be less than the divisor. Why I'm explaining this? Because this division of polynomials, and then further when we discuss the remainder theorem and factor theorem, there will use these concepts. Okay, so make sure one thing what we have got is whenever we are dividing any positive integer by another one, then we'll get two unique integers. One is q and r, that will always satisfy this. Means dividend is equal to divisor into quotient plus remainder, and the remainder might be either 0 or more than 0, but it must be less than the divisor. This result we call as division lemma. The same result we are going to use in the division of polynomials as well, right? So let me just take a few examples of division of polynomials, and then we'll explore how we can divide the polynomials and how we can use this result. For example, if I'm taking this polynomial 3x square plus x minus 1, and I'm dividing this by a linear polynomial x plus 1. X plus 1. So the very first thing is this is a quadratic trinomial. So quadratic in the sense of degree of this polynomial, and trinomial in the sense of the number of term. And this is linear binomial. Linear because of the degree, and the number of term is 2. So this is linear binomial. So how we can divide this polynomial 3x square plus x minus 1 with this linear x plus 1? So we'll first, one thing we need to look over here. So we need to first check the first term and the first term of this divisor. So here, whatever be the divisor we have, once we multiply divisor and quotient, make sure the degree of these two products will be equal to the degree of the dividend. So here we have 3x square, and here the first term is x. So try to divide this term 3x square with the first term over here. So that is going to give us 3x square divided by x is nothing but 3x. Means we'll get 3x square only if we multiply x with what? This 3x. So write down over here 3x. Now this 3x is the quotient. This 3x is going to multiply with this linear polynomial, linear binomial. That is going to give us x times 3x is 3x square. Now this 3x is going to multiply with the second term over here, which is plus 1. So 3x plus 1 is 3x times plus 1 is nothing but plus 3x. Now subtract this. How we can subtract? So whatever be the expression we are getting in the, like over here, we need to revert the sign, as this is plus goes to minus, this is plus goes to minus. Now this plus 3x square minus 3x square got cancelled. Here this is plus x and here this is minus 3x. So when we are adding both of this, that is going to give us minus 2x. Now copy this number, -1. So likewise we got the first term of the quotient. In order to look for the second term, again we need to follow the same process. What is the first term here? -2x. What is the first term? X. So divide this -2x by x. That is going to give us -2. Means we need to write -2 over here. This -2 is going to multiply with both of this term. So once we multiply this, we'll get it as -2x and -2. When we multiply -2 with x, -2x, -2 with 1, that is -2. Again subtract this. So for subtracting we need to revert the sign, minus goes to plus and this minus to plus. So this minus 2x and this plus 2x got cancelled. This is -1, this is plus 2. -1 plus 2 is what? Plus 1. So here we found that when we are dividing this polynomial 3x square plus 1 plus x minus 1 with x plus 1, we are getting the quotient as 3x minus 1 and the remainder as 1. So here the quotient is, we are using q for the quotient and r for the remainder. So qx is equal to 3x minus 2 and rx is nothing but is equal to 1. 1 is a constant, so this is a constant polynomial. So one thing is clear, that we can cross verify this result. We can cross verify this result by using the division lemma. Check it whether this 3x square plus x minus 1 is equal to the product of these two plus this or not. So let's try to verify. So over here this is the divisor, so x plus 1 and the quotient is 3x minus 2. Okay, and then the remainder is plus 1. Try to simplify this and check what values of this expression we are getting. Are we getting the same 3x square plus x minus 1 or not? If we are getting, means we are done, right? So how we can multiply the polynomial? So it's like a distributive property. This first term with this whole polynomial, x times of 3x minus 2, then 1 times of 3x minus 2 and plus 1. Once we simplify, this is going to be 3x square minus 2x plus 3x minus 2 plus 1. So this is going to be 3x square minus 2x plus 3x is plus x and minus 2 plus 1 is minus 1, which is equal to nothing but the given dividend. And also one more thing we need to notice over here, as in the case of the integer, we have gotten like the whatever be the values of remainder, that is either 0 or it must be either equal to 0 or bigger than 0, but must be less than the divisor. But here in this case, in a division of polynomial, the remainder might comes a constant polynomial or a zero polynomial or a polynomials in any degree that must be less than the degree of the divisor. Here we can find that the degree of this divisor is 1. It means the degree of the remainder should be 0. If this is divisor is quadratic, then the remainder must be a linear. If the divisor is cubic, then the remainder should be a quadratic. Okay, so this is the way we are doing the long divisions of polynomial. Let's try to explore one more example where we'll use the divisor as a quadratic and dividend as a biquadratic. So let's say we have a dividend as 6x power 4 minus of x plus 2x square minus 1, and the divisor is given as x square minus 2x plus 3. So we have given this biquadratic polynomial and the divisor as a quadratic polynomial. Now one thing we need to take care while dividing a polynomial using long division method, make sure this dividend should be written in a standard form. As here we can find that this is a polynomial of degree 4, but this is not written in a standard form. A standard form, already you know that the orders of the powers of the variables is in decreasing order, right? So here we can find that power 4, power 1, power 2. So we can write this in a decreasing order of the powers with the presence of those all terms. Like here we can find that the xq term is missing. So we can write the xq term as a coefficient 0. So we can write this biquadratic as 6x power 4 plus 0 xq. As xq term is missing, so we can write this as a coefficient 0. Now 2x square minus x then minus 1. Now this is our dividend. We can now divide this by the quadratic, which is x square minus 2x plus 3. Now in order to divide this biquadratic with this quadratic, what we need to do, we need to just look into the leading term. So the leading term is 6x power 4 and the leading terms of the divisor is x power 4, x power 2. So 6x power 4, if we are dividing by the first term of this divisor, we'll get it as this x square cancel this x power 4 as x power 2. So this is going to be equal to 6 times of x power 2. So we can write this as 6x power 2. Now this 6x power 2 is going to multiply with each term in the divisor. So once we multiply this 6x square with this x square, that is going to give us 6x power 4. Then minus 2x multiplied by 6x square is going to give us minus of 12x power 3. Then plus 3 times 6 is plus 18x square. Now we need to subtract. In order to subtract this, what we'll do, we'll see the sign of these expression, these polynomial, which I have written over here down this, right? So in order to subtract this, we need to just change the sign of each term over here. So as this is plus, change to minus, this minus change to plus, this plus change to minus. Now the sign of these terms are this one, blue one. This one is minus, this one is plus, this one is minus. So now we are operating these two. This is plus, this is minus. Plus minus, same coefficient of the x power 4 got cancelled. Now here this is plus x cube plus 12xu. So 0 plus 12 is nothing but 12x cube. Now here 2 minus 18 is going to be negative 16x square. Now we can copy the rest of the term. So the rest of the term is negative x and negative 1. So that is negative x, negative 1. Now ask the question from yourself, whether is this done or we need to go for one more step. So make sure whenever we are dealing with the division of the polynomial, the reminder's degree should always be less than the degree of the divisor. Here the divisor is quadratic. It means we need to proceed until unless the remainder is not coming as a degree 1. Okay, so let me just go ahead. What we'll do, once again we'll go with the same process. Now this is the leading term and we are going to divide with this again. So what we'll do, we'll divide the first term of this leading term of this polynomial by the leading term of this divisor. So once we divide this 12x cube by x square, so 12x cube over x square is going to give us 12x. Now this is plus, so this is plus, this is also plus, so the result is plus. So we need to keep it as plus 12x. Plus 12x. So now this plus 12x is now going to multiply with all these terms. So multiply this 12x into x square is 12x cube. Now plus 12 minus 2 means minus 24. X into x is x square. And then last plus 3 into 12 is plus 36x. Then again we'll do the same process. what we'll do, we'll subtract this. So for subtracting this, we need to change the sign of this, all this term. So here this plus 12 goes to minus 24 is plus 36 is minus 36. Now you see both are having same coefficient, alternate sign got cancelled. Here this is negative 16, this is plus 24. So 24 minus 16 is plus 8x square. And this is minus 36 minus 1 is minus 37x. And the last term is negative 1, will copy over here. Once again see, the degree of this remainder is still equal to the degree of the divisor. So further we can divide this. So again we'll do the same process. First term, leading term is 8x square, right? So this leading term we are going to divide with this leading term of this divisor. So 8x square is going to divide by x square, that is going to give us 8. So plus 8 is the number over here. So this plus 8 is going to multiply it with all of this term from this divisor, that is going to give us 8x square, then negative 16x, then plus 24. Subtract this, so change the sign, plus to minus, minus to plus, and plus to minus. This got cancelled. Now this is negative 36 plus 16. So alternate sign we need to subtract. Subtract from 37, like 37. That is going to give us 21. And that too in negative, because the sign of this bigger one is negative. So negative 21x, and this is negative 25. So now ask question from yourself whether we need to stop over here or can we go for one more step. The answer is no, this is the final step, because the degree of the remainder is less than the degree of the divisor. So this is the remainder, and the quotient that we got over here is this one. So the remainder is negative 21x negative 25, and the quotient is 6x square plus 12x plus 8. One more time you can cross verify this by using the divisor into quotient plus remainder. I mean dividend is equal to divisor time quotient plus remainder. So you will find that when you are multiplying the divisor with this quotient and then adding this remainder is going to give you back the given dividend. Okay, one more thing need to be noticed over here. The degree of the dividend is equal to what? Degree of dividend in any division of polynomial is always equal to the degree of the polynomial obtained upon multiplying the divisor and the quotient. Okay, so this is a very important point. Take a note of this. Now the very important topic in this polynomial chapter is the remainder theorem and factor theorem. So I'm now going to start the remainder theorem. In that we'll discuss the remainder theorem statement, then we'll go for its proof, and then we'll solve a couple of problems. So let me start with the statement first. Remainder theorem. What it says. So let's say P be any polynomial of degree greater than or equal to 1. Let Px be any polynomial of degree n greater than or equal to 1, and A be a real number. A be a real number. So first of all, P is any polynomial of degree n which is either 1 or greater than 1. This symbol is greater than or equal to implies what? Either n is equal to 1 or it is bigger than 1. It might be 2 or 3 or 4 or 5, whatever be, and a be a real number if px is divided by the linear factor x minus a, then remainder is PA. So here, if the polynomial of degree n, which is 1 or bigger than 1, is divided by the linear factor, which is x minus a, means why linear? Linear in the variable x. The power of the variable x is 1. That's why this expression we call as a linear. Okay. So if we are dividing any polynomial, this polynomial of any degree of any coefficient or whatever be the real coefficient, right? Okay. Then in that case, if we are dividing this px by x minus a, then we can find the remainder is equal to the value of the polynomial at the value of the variable x is equal to a. So for example, I'm just giving you an idea, then we'll go for the proof of this. Let's say we have given a polynomial px, which is given as x square minus 2x plus 1. This is a polynomial, or let me make it plus 3. So if we are dividing this polynomial by this x minus 2, means we are dividing it by x square minus 2x plus 3, then we'll find the remainder that will be equal to nothing but the value of the polynomial at x is equal to 2. So usually when we are finding the remainder, we are using the long division method. We are choosing the possible quotient over here, and then at the last we are finding the remainder. But using the remainder theorem, we are going to find the remainder by substituting the values of x, okay, at x is equal to means if x minus 2 is dividing this one, means we'll keep this value x minus 2 is equal to 0, we'll get the value of x is equal to 2. At this value, the polynomial value will be nothing but the remainder of the polynomial. In this case, we can find, as we are getting x is equal to 2 is the value of this, means x square minus 2x plus 3, we are dividing by x minus 2, then the polynomial will be nothing but p2. Substitute x is equal to 2 in this, we'll get it as 2 power 2 minus 2 times of 2 plus 3. That is going to give us minus 4 plus 3, 4 cancels, 3 is the remainder. So 3 is the remainder. We can cross verify by doing the long division as well. Let's check. Here x square is the leading term, here x is the leading term. If we are dividing x square by x, that is going to be x. Then x is multiplied by both of this term, that is going to give us x square minus 2x. So simplify this, that is going to be cancelled, remainder is 3. Right. So this remainder theorem suggests that whenever we are dividing a polynomial of any degree which is either 1 or bigger than 1, okay, then in that case, by a linear factor of this format, x minus a format, then the remainder is p of a, where a is nothing but any real number. So let's see the proof, and then we'll solve couple of questions based on this theorem. So first of all, whenever we are dividing, as already we have seen that whenever we are dividing any polynomial by any divisor polynomial, we'll always get two unique polynomial. One is quotient polynomial as well as one is remainder polynomial, right? This already we know, right? I discussed in the very beginning of this lecture, right? So over here we are dividing this polynomial by x minus a, means this px is going to be the dividend, px is dividend, and the divisor is what? x minus a. Then obviously we'll get two unique polynomial. One is quotient polynomial, let's say qx, and one is remainder polynomial, which is rx. And the remainder will be, the degree of the remainder will be less than the degree of the divisor. As here the degree of the divisor is 1, it's a linear, then the remainder must be a constant. So for that I'm just writing it a r. Now with the help of the division lemma, like dividend can be written as the product of divisor into quotient plus remainder. So we can write this as px is equal to x minus a times qx plus r is the remainder, right? Our aim is to find the remainder, which is pa, right? Now let's try to find the value of this polynomial at x is equal to a. So if I'm substituting x is equal to a, if I'm substituting x is equal to a in this polynomial, then that is going to give us what? PA is equal to, in place of x, if I'm substituting a, so a minus a, and this is QA, and r is a constant, so this will be r is nothing but remainder over here, right? So this a minus a is 0 times of QA, 0 times of QA plus r is equal to PA. So 0 times of anything is 0, so this is basically 0 plus r, and 0 plus any number is again the same number, means this is what? This is equal to r. So PA is equal to what? R is nothing but the remainder. R is nothing but the remainder. So whenever, here as in this case we got PA is nothing but the remainder. So whenever we are dividing any polynomial by a linear factor, then that polynomial will give, in that case we'll get the remainder as the value of the polynomial at x is equal to a. I hope this is clear, okay? So let's see one more example. Suppose we have given a polynomial px is equal to x power 3 minus of 2x plus 1, and we are going to divide this by let's say ax, which is equal to x plus 2, x plus 2, right? So what will be the remainder in this case? What is the remainder? So we need not to go for long division method, we just need to use the remainder theorem, as this is a linear, divisor is a linear, and this is obviously this is in the format of x minus a, because this plus 2 we can write it as x plus, x minus 2. So this is what? Minus a is real number, minus 2 is what? A. As a is real number might be positive, negative, decimal, right, of fractions, or inside root, irrational number, right? So this is what? Ax is equal to x minus of minus 2. It means when we substitute this is equal to 0, we'll get the value of x is equal to minus 2, means the remainder of this variable, like in this case, is the value of the polynomial at x is equal to negative 2, right? So when you substitute this is equal to 0, then you will find that the value of x is going to be equal to ax is equal to 0, means x plus 2 is 0, so x is equal to negative 2 is the value of x, that if we are substituting in this, we are going to get the remainder. So substitute this, minus 2 power 3, minus 2 times of minus 2 plus 1, so negative 8, negative is positive 4 plus 1, so this is going to give us minus 3 is the remainder. I hope this is clear. So we'll explain few more example based on the remainder theorem, and then we'll move to the factor theorem. Now suppose px is equal to 3x power 2 minus of 5x plus 7 is divided by bx is equal to 2x plus 7. Then find remainder. find remainder. If px is 3x square minus 5x plus 7 is divided by bx, which is 2x plus 7, then what will be the remainder? So here we can find that this bx is a linear invariable x. So whenever we are dividing a polynomial by a linear factor of the form x minus a, okay, when we are dividing a px by a linear factor of this form x minus a, then remainder will be pa. But this does not look like this, right? So we can find that here the format of this is what? X minus a, where the coefficient of x is 1, but here we have coefficient of x is 2, and also here we have subtraction, but here we have addition. So can we get this factor in this form? Obviously we can get, right? So first what we can do is we can make the coefficient of x to be 1 by taking the 2 as a common. So by taking 2 common, this will become x plus 7 over 2. X plus 7 over 2, right? Now further we can find that this plus we can write it as x minus of minus 7 over 2. So it means by dividing this px by 2x plus 7, it means we are dividing it by 2 times of x minus negative 7 by 2. So now this is a what format? This is a format x minus a. So what is a over here? So a is negative 7 over 2. So the remainder in this case is going to be p negative 7 by 2. So remainder is equal to what? Remainder is equal to p negative 7 over 2. Now substitute the value of x negative 7 by 2 in the given polynomial. We are going to get it as 3 times of negative 7 over 2 power 2 negative 5 times negative 7 over 2 plus 7. Now we can find it as 3 times of 7 square is 49, 2 square is 4, as negative square is positive, so this is going to be 49 by 4. And this negative is positive. 5 7s are 35 by 2 plus 7. Further we can simplify this as 3 9 times 27. Remainder 2. 3 4 times 12 plus 2 is 14. 147 over 4 plus 35 over 2 plus 7. So now this is a simple additions of fraction by taking the LCM of the denominator 1, 2 and 4, which is going to be 4. We can write it as 147 plus 70 plus 28, which is going to just add this simply. Add 7 is 15, remainder 1. Now 7 plus 2, 9 plus 1 is 10, 4 14, remainder 1, right? Then 1 plus 1 is 2, 245 by 4 is the remainder. So this is the way, whatever be the form that linear factor is given, we can convert that into the form of x minus a. If we are unable to convert in that format, we can directly substitute this value is equal to 0 and we can find the value of x by solving this, and that value of x we can substitute in the polynomial. That is going to give us the remainder. So let's try one more example where we can simply find the remainder by equating the linear factor equal to 0 and find the value of x. That's the same thing, like we are converting this into x minus a form. So it might be sometimes tedious how we can we are taking 2 common or whatever be. So instead of doing all this thing, we can just equate this linear to be equal to 0 and find the value of the variable from here and then substitute that value into the given polynomial. So let's take another example. Px is equal to 3x power 4 minus 2x plus 5, and we are going to divide it by 1 by 3 times of x plus 5. So as we can find in this case, we are going to divide this px, which is a biquadratic, by a linear factor. So we can easily find the remainder by finding the value of x from this linear by equating it to 0. So when we equate it to 0, 1 by 3 times of x plus 5 is 0, is going to give us x over 3 is equal to negative 5. Then x is equal to 3 and 5 is going to multiply, which is equal to negative 15. So we can easily find the value of this px at x is equal to negative 15. So just substitute this value. Our remainder is equal to 3 times of, or just substitute this p negative 15. So 3 times of negative 15 power 4, negative 2 times of negative 15 plus 5. Right. So over here we need to find the 15 power 4. So as you can remember, the square of 15 is 225, right? So as first of all, this is negative power is even, means this will be positive. So I'm just writing it as negative, 3 times of 15 is square of a square, means 15 square is 225 times of 225. I'm just writing this as 15 power 2 into 15 power 2, and then negative is positive. 15 2 times 30 plus 5. So this is 3 times of 225 times of 225 plus this is 35. Now further you multiply these two and then add to get the required remainder. So after solving this question, write down the answer in the comment box. This is question number, mark it as question number star. Okay, so while commenting, write the comment like a star. Answer is whatever the final answer you are going to get after simplification of this. So let's try to solve one more question based on this remainder theorem, and then we'll move to the factor theorem. If fx is equal to k times of x square minus 2x plus 3 is divided by gx is equal to x plus 1, gives remainder or remainder 3. Then find the remainder if fx is divided by hx is equal to 1 by 2 times of x minus 1. So we have given a quadratic polynomial fx, which is k times of x square minus 2x plus 3 is divided by gx, gives remainder 3. Then we need to find the remainder if fx is going to be divided by the linear factor hx. So first of all, when fx divided by this linear factor, then the remainder is given by what? When we substitute in place of x, like if we substitute this is equal to 0, means gx is equal to 0. This is going to give us x plus 1 is equal to 0, means x is equal to negative 1. When we substitute this x is equal to negative 1 in this fx, that means that is the remainder, and already the remainder in this case is given as 3. So we can say that f negative 1 is given as 3. F negative 1 at x is equal to negative 1 means when we are dividing this fx by gx, then in that case the remainder is what? X, means f value at x is equal to -1. Okay, now substitute this value of x -1 in the given polynomial k times of x square. So k times of x is -1 square minus 2 times of -1 plus 3 is equal to 3. So -1 square is plus 1, plus times of k is k, and this is minus is plus 2, and plus 3 is equal to 3. Once we simplify this is 3 and right side 3 is going to cancel, or just simplify this. 3 plus 5 is equal to k plus 5 is equal to 3, so k is equal to -2. Now we got the value of k, substitute this in the fx, and then again follow the same process. Now this time the fx is what? Fx is equal to k is what? -2. So this is -2x square minus 2x plus 3. Now this time this is going to be divided by hx, which is 1 by 2 times of x minus 1. So finding the remainder in this case, so we can find the value of x by substituting this equal to 0. That value of x going to substitute in the given polynomial fx, that will give us the remainder. So when we substitute hx 0, it means 1 by 2x minus 1 is 0, means 1 by 2x is equal to 1, means x is equal to what? 2, means the remainder in this case is what? f2 is the required remainder. So remainder is equal to f2 means what? -2 times of 2 power 2, -2 times of 2 plus 3, which is 2 power 2 is 4, 4 to the 8, -8, and -4 plus 3, so this is equal to -12 plus 3, which is -9. So this way we can solve the question based on the remainder theorem. Will give the worksheet, in that you all can find the different kind of problem which is up to some higher level than this one. This is just the basic understanding of this remainder theorem. Okay, so now next move it to the next part, which is the factor theorem. Factor theorem. Let's first try to understand the statement of this theorem, and then we'll go for the proof of this, and then couple of examples based on this. So what it says that if px is a polynomial of degree n, which is either 1 or bigger than 1, and a be any real number, then x minus a is factor of px. IFF, this is if and only if PA is equal to 0. This IFF is written in short for if and only if. Or you can write directly this if and only if. So it means what? This if and only if means what? If this is the one statement, if this is a factor, then this will be the result. I mean, if x minus a is factor of px, then the value of the remainder will be 0. Pa means what? Remainder will be 0. Or another way, if we say if pa is equal to 0, then x minus a will be the factor of px. So let's try to break down this statement into two parts. What it means, we need to look into this two like condition for this factor theorem. What it says that if pa is equal to 0 means then x minus a is factor of px. Means for any polynomial at x is equal to a, if we are getting value of polynomial be 0, then in that case x minus a will be the factor of the polynomial px. And in another way we say that if x minus a is a factor of px, then pa is equal to 0, then the value of the polynomial at a will be 0. So this is exactly the meaning of this factor theorem. So let's see the proof for this theorem. Let me just give the proof for the first part. Now here, if PAA is 0, PA means what? The value of the polynomial at x is equal to a is 0, then x minus a is factor of px. Let's suppose we are dividing this px by x minus a, then we'll get two unique polynomial. One is quotient polynomial, one is remainder polynomial. So we can write by using the Euclid division lemma for the polynomial that px is equal to, we are dividing by x minus a, then we'll get a quotient, any quotient, right, for any variable x, for the variable x we'll get the quotient, right? So here we are dividing by x minus a, px, then obviously we'll get a unique quotient as well as a remainder, right, as well as a remainder. As here this we are dividing by a linear, factor, so the remainder will be a constant. So this is what? A remainder. Now we have given one condition. If PA is 0, then x minus a is a factor of px. So when we can say that this is factor of px, then x minus a is going to completely divide this px, means the remainder we are getting 0. If we are getting the remainder 0, it means what? This x minus a is completely dividing this px, right? So now as we have this one, means px is equal to x minus a times qx plus r is any constant, right, any remainder, this is remainder, right? Now with the given condition at x is equal to a, pa value is 0, so substitute x is equal to a over here. So when we are substituting at x is equal to a, the right side will be equal to a minus a times qa plus r. So as this a minus a is 0, 0 times of qa is what? Again 0. So 0 plus r is equal to pa, right? And the given pa value is 0. It means what? Pa is equal to r, means remainder is equal to pa, but pa is given 0, it means remainder is 0. So when we are dividing this px by x minus a, we are getting remainder 0. It means what? X minus a is completely dividing the polynomial px. It implies what? X minus a is factor of px. I hope this is clear, right? Now let's see the second part, proof for the second part. So this is the proof of the first part. If x minus a is a factor of px, then we need to prove that pa is equal to 0. So x minus a is a factor of px. It means what? When we divide px by x minus a, we'll get remainder 0, right? Then only we can say this is factor. When x minus a is completely dividing px, then only we can say this is a factor, right? So we can write the proof for this second part as, when we are dividing px by x minus a, we'll get quotient as well as remainder, but in that case we'll get remainder as 0 because this is completely dividing px, right? So here we'll get it as px is equal to x minus a times of some qx, this is the quotient, and the remainder will be 0. It means this is basically px is equal to x minus a times of qx, which is what? X minus a times of qx. what we need to prove? We need to find the value of PA. Then in that case PA will be 0. So just substitute in place of x A and then find what value of PA we are going to get. So when we substitute x is equal to A in this, then this will be PA is equal to A minus A times of QA, and A minus A is 0. 0 times of anything is again 0. It means what? PA is equal to 0, and we are done. Right. So this is the proof of factor theorem, which is having two results, if and only if condition. First condition is if PA is 0, then x minus A is factor, and if x minus A is factor of Px, then PA will be equal to 0. Now let's see some example based on this. The question is, check x minus 3 is factor of Px is equal to x square plus x minus 6. Check x minus 3 is factor of Px is equal to x square plus x minus 6 or not. So if x minus 3 is factor of Px, then by the factor theorem the value of P at x is equal to 3 will be 0. So we need to just check whether the value of this P at x is equal to 3 is coming 0 or not. If it is coming 0, it means this x minus 3 is factor of this. So what we'll do, we'll equate it to 0 and find the value of x from here. We are going to get x is equal to 3. Now substitute this value of x in this and find this P value at x is equal to 3. So which is going to be 3 square plus 3 minus 6. So which is 9 plus 3 minus 6. So 12 minus 6 is 6. So we are getting P3 is equal to 6, which is not 0. It means x minus 3 is not factor of Px. X minus 3 is not factor of Px. Now let's see another example. Check whether x plus 1 is factor of Px is equal to 3x cube minus 12x square plus x minus 9x square plus 12. Check whether x plus 1 is factor of Px or not. So in order to check whether this is factor or not, what we need to do, we need to equate it to equal to 0 and find the value of x from here. When we equate it to 0 and then we'll get x is equal to minus 1, right? So when we equate it to 0, x plus 1 0 means we'll get x is equal to minus 1. So we need to check whether the Px at x is equal to minus 1 is equal to 0 or not. If it is 0 means x plus 1 is factor, if not means x plus 1 is not factor. So let's substitute x is equal to 1 minus 1. When we substitute x is equal to minus 1, this is 3 times of minus 1 power 3 minus 9 times of minus 1 power 2 plus minus 1 plus 12. So this is going to be negative 1 to power 3 is negative 1 times of 3 is negative 3, and this is negative 1 square means positive 1 into 9 is positive 9, and this is minus, so negative 9, and plus minus is minus 1 plus 12. So when we add all these things, 9 3 is 12 minus 1 is minus 13 plus 12, which is equal to negative 1. So P negative 1 is equal to negative 1, which is not 0. It means x plus 1 is not factor of this polynomial Px. I hope this is clear. So just go through all the concept and the theorems that I have discussed, and based on the problem that are the basic questions for the understanding of the theorems. In the next lecture, that will be the lecture number 5, in that we are going to discuss the problem based on the remainder theorems and the factor theorems, and the question will be more on like the Olympiad level. So make sure to understand the concept that I discussed in lecture number 3 as well as lecture number 4. Stay tuned, we'll meet in the next video.